The force exerted on a pulley. A 12 kilogram box that I have labeled number 2 here, resting on a horizontal frictionless surface, is attached to a 5 kilogram weight, that's mass number 1, by a thin light wire. It's a light wire that passes over a frictionless pulley. You can see in the figure. The pulley has the shape of a uniform solid disc of mass 2 kilograms and diameter 0.5 meters. After the system is released, find part A, the tension in the wire on both sides of the pulley. So the tension on this wire and tension on this wire. Part B, the acceleration of the box. The acceleration of the box. And part C, the horizontal and vertical components of the force that the axle exerts on the pulley. Horizontal and vertical components. Okay. So let's start with remembering that for a uniform solid disk, this is the result of problem 9.53, the moment of inertia for a pivot at the center of mass is capital M, capital R square over 2. So M is the mass of the disk, capital R is the radius of the disk. So if we apply this here, in this case for the pulley, I center of mass will be equal to, the mass of the pulley was 2 kilograms and diameter is 0.5 meters. So it will be 2 times the radius square 0.5 divided by 2 square divided by 2, mr squared over 2. So this gives us 0.0625 kilograms meter square. So we have calculated the moment of inertia for rotations about the center of mass axis for a uniform solid disk. So that's our pulley. Now let's concentrate for part A and part B, free body diagram of the 5 kilogram block. So that's this block here. On this block, we have the tension on this wire and the weight pointing down. So we can put here T1, the tension in the first wire, and M1G, the weight of the block. And if this is our y-axis here, we can see that the net force on the y-axis will be the tension T1 minus M1G, which is responsible for the acceleration of this mass, because it will accelerate down. It's in minus j hat direction, so it's minus A1A. So we can see that tension T1 is equal to M1G minus M1A in j hat direction. Now if we concentrate on the 12 kilogram block, we have the weight of this block, the normal force exerted by the horizontal surface, and the tension on the second wire, that will be T2. There could be friction here, but it's a frictionless surface, so there is no friction. So we identify the forces as the weight, M2G, the normal force, N, and tension on the second wire, T2. And if this is our x-axis, net force on the x-axis is just the tension T2, which is equal to M2 times the common acceleration A of M1 and M2. Now I want to look at the free body diagram of the pulley. Well, the pulley is in contact with two wires, so there will be tension T2 and tension T1 acting on it. And because it's also in contact with this axle here, there will be a horizontal component and vertical component of the force acting on it. So if you concentrate on the pulley, you will see that the pulley, first of all, has a mass capital M multiplied by gravitational acceleration G, the weight pointing down. That is our gravitational force. And there is the tension on the first wire, T1, pointing down because it was pointing up on mass M1. It is pointing down on the pulley. And likewise, we have a tension T2 on the second wire. And then we have a force here that is exerted by the axle. So this is our contact force that we can see due to the physical contact between the axle and the pulley. So if we set up our coordinate axes here, this is x-axis, y-axis, and z-axis, you can see that the net torque acting on this pulley, the torque is R cross F. So if the pivot is at the center, we have R2 vector, the position vector of the application point, cross with T2 gives us a torque in plus k hat direction using the right hand rule. We point in the direction of the point of application of the force with our right hand, curl our fingers towards the force T2, the thumb points out of the page. So the torque that we find here is the radius capital R, tension T2 in k hat direction. And for T1, we have the position vector of the application point, that is the tangential point here on the x-axis. So R1 cross T1, we point our right hand towards the application point, curl our fingers towards T1, the thumb points into the board, so the torque is in minus k hat direction. So this is minus R T1 k hat. So we obtain a net torque R T2 minus T1 in k hat direction. So that's going to be equal to I alpha. Now we can choose a direction for our alpha. If the alpha is pointing in the clockwise direction, you can see that the alpha vector would be pointing in minus k hat direction. So this would be equal to minus I center of mass alpha k hat, where alpha is now the magnitude of this angular acceleration, and the tangential acceleration A is related to angular acceleration alpha times capital R. So the torque R times T2 minus T1 is equal to minus 1 over 2 capital M R square, which is our I center of mass, times alpha. Alpha is magnitude of the acceleration, A divided by R. So this R and this R will cancel, and we will be left with one more R here. So this R will get rid of the remaining R here. So we will be left with T1 minus T2 is equal to MA over 2. Notice that I have applied the minus sign to the left hand side, so it's not T2 minus T1, it's T1 minus T2. Now let's recall T1 is M1G minus M1A, so we have M1G minus M1A, and T2 is equal to M2A minus M2A is equal to capital MA over 2. The mass of the pulley times acceleration divided by 2. Now we can basically gather all the terms that have A in them on the right hand side. So I will pull A and put everything on the right hand side. So left hand side I will be left with M1G only. So I will have M1G is equal to A times, so let's see what we have, capital M over 2. So we open up a parenthesis here. The first term is capital M over 2. The second term is M1 and the third term is M2. So plus M1 plus M2. So we find that the magnitude of the acceleration, common acceleration, will be m1g divided by capital M divided by 2 plus m1 plus m2. So if we substitute the numbers here, m1, the mass of our weight that is hanging here is 5 kilograms. So we have 5 times gravitational acceleration 9.8 meters per second square. Capital M was 2 kilograms. That's the mass of the pulley. So it's 2 divided by 2 plus M1 again. We have 5 kilograms and M2 is mass of our block, and that is a 12 kilogram block you can see here. So we're going to put 12, and this gives us 2.72 meters per second square. So that's the acceleration, and to find tension we have to substitute this result into this equation and this equation. So tension on the first wire, T1, is M1G minus M1A. So it is 5 times 9.8 minus 5 times A. This gives us, if we substitute for A, 2.72 meters per second square, 35.4 newtons. With 3 significant figures. And as for T2, we have T2 equals M2 times A, which is 12A. So this gives us 32.7 newtons. Now you might wonder why we have 2 different tensions here. Well, as you can see, this pulley has a mass, so it's going to feel a torque due to these 2 tensions. If these 2 tensions were the same, there would be no torque on this pulley and the system would not be rotating. So the pulley would not be rotating. So in order to ensure we have a rotation here, we need to have a T1 which is greater than T2 so that there will be a net torque in the clockwise direction. Okay, to cause a clockwise rotation. Now for part C, we want to know the horizontal and vertical components of the force. Now go back to the pulley free body diagram you can see here. Now let's write the net force on the x-axis. So the net force on the x-axis from the pulley free body diagram is the horizontal component of the force exerted by the axle, I will call H, and there is a T2 pointing in negative I-hat direction. H minus T2 is equal to 0. So the horizontal component of the force on the axle should be equal to T2, which is 32.7 newtons. And vertical component I will call V, the contact force. The net force on the y-axis should be equal to, now let's see here, we will have a component of this force, V, mg and T1 pointing down. So we will have vertical component minus T1 minus capital Mg. This must be equal to 0. And therefore, we find that the vertical force is equal to T1 plus mg. So this would be 35.4 newtons plus 2 kilograms times 9.8 meters per second square, which will give us 55.0 newtons when reduced to 3 significant figures. So basically, what I have done here is I labeled the components of this force on horizontal and vertical axes. All right. So let me make this a little bit smaller here. So this component I have here is the horizontal force, and this component I have here is the vertical force. Okay, so this horizontal and vertical components are the components of the force, this red force exerted by the axle. So this force I can label basically force exerted by the axle. Okay, so it's F axle. All right, so let's summarize what we did here. We have two masses, 5 kilogram mass M1, that is hanging from this light wire that passes over a frictionless pulley, but the pulley has the shape of a solid disc. It has a mass, 2 kilograms, and diameter 0.5 meters. So as the system descends, as this mass descends, you will see this pulley will turn and the string will pass over the pulley. Now this mass M2 is 12 kilograms. It's on a frictionless horizontal surface, and it's only under the influence of this tension on the x-axis. So we want to know the tension in the wire on both sides of the pulley, the acceleration of the box or this mass, they accelerate together, horizontal and vertical components of the force that the axle exerts on the pulley. So these components I can also show here. We have a horizontal force and a vertical force. This is horizontal force H, vertical force V, and as a result I have this force which I have labeled F axle here. Okay. All right, so I recall the result for a uniform solid disk. The center of mass rotations for the center of mass pivot point is capital MR squared over 2. So I start with drawing the free body diagram of the 5 kilogram block. I see tension T1 and weight M1G pointing down, T1 and M1G, which gives me T1 minus M1G is minus M1A because it will accelerate downward. A is the magnitude, then I will have minus M1A J hat for this force. So T1 is M1G minus M1A. For the 12 kilogram block, I have M2G, the normal force, the tension on the second wire T2. So T2 is M2 times A. That's the only force on the x-axis. When I concentrate on the pulley, I have T1 pointing down, T2 pointing to the left, the weight pointing down, capital Mg, and then there is the contact force, vertical component, horizontal component, acting on it. If I write the net torque acting on this pulley, it's RT2 K hat minus RT1 K hat. The directions I have found using the right hand rule by pointing my right hand towards the application point of the force, curling my fingers towards the force, and watch where my thumb points. And net torque is equal to I alpha. Well, I have defined this direction of alpha in minus K hat direction, alpha vector. So using my right hand, if I curl my fingers towards alpha in the clockwise direction, my thumb points in minus K hat. So that is minus I center of mass alpha K hat. And the relationship between angular acceleration and tangential acceleration is A is equal to alpha times R. So that's the result I have here. So by writing the torque equation, rotational form of Newton's second law, I obtain a relationship T1 minus T2 equals ma over 2. And for T1 I substitute this result, for T2 I substitute this result and isolate acceleration, and I can find its numerical value by plugging in the numbers. Then I can use my acceleration in T1 and T2 equations to calculate the tensions. In order to figure out the contact force on the pulley, I write the equilibrium condition on the pulley because the pulley is not moving, it's actually only rotating. Translational force on the x-axis is H minus T2 is equal to 0. On the y-axis is vertical force V minus mg minus T1 equals to 0. So by plugging in T1 and T2, I can find these horizontal and vertical components of the axle, the force of the axle. And because this force is exerted on the pivot point, it has no torque effect. It would only have translational effect, but we have equilibrium situation, so net force on the x and y axis should be 0.